All right, so this is the demonstration for if you have two open ends or two free ends. So this is the situation where I have two free ends, so it should have an antinode, antinode. So as I swing this around, it makes a sound. All right, those are what you're hearing are the various harmonics, and what we're going to do is we're going to actually predict them and match it up to the frequency of this, just to see how close that we get. And so a couple things here, and how does it actually work? So as I swing this around, the tip down here is not moving very fast, but the tip up here is. As this tip is moving faster, the air pressure at the entrance right here is less than the air pressure down here, and so basically air gets sucked up through it. And so that's why you have air going through it, and then the ribs here are in order to get the air to actually vibrate. You can make the sound also without the ribs, but you don't get the whistling sound. Another thing to keep in mind is we found this in our backyard in the first house that we ever owned. There was, I still suspect there's a dead body back there somewhere, but we never found the dead body. We did find a barbell set buried under the ivy, and we found this as well. So I'm throwing in, you can still see the dirt on some of it. There you go, close up of the dirt because it had been buried. So I'm setting up my excuses now if it's not perfect, but it actually is a lot closer than I would think. Another thing to keep in mind is as we spin it, we are going to have to measure the length of this, and the length does change a little bit. It does stretch out some, so I'm just going to give it a little bit of a stretch when I actually measure the length. Another thing to keep in mind is we actually don't hear the first harmonic. If in order to spin this slowly enough to get the first harmonic, there's not enough of an air pressure difference to suck enough air up through it or with enough velocity, and so what we end up with is that's the second harmonic, third, fourth, and then there's a fifth up there, which is really difficult to hear. It sounds mostly like wind instead of the whistling. So we're going to stop it here and come in later with some more math. So the speed of sound, there's a formula more specific that's related to temperature, is equal to 331.3 meters per second times the square root of the temperature in Kelvin over 273.15. The temperature where we are right now is about 75 degrees Fahrenheit. To convert that into degrees Celsius, I have degrees Fahrenheit, degrees Fahrenheit and degrees Celsius. I know that when this is 32 degrees Fahrenheit, this is 0 degrees Celsius, and I know 212 is the boiling point and 100. So if I connected those, that the slope of that line is rise over run, so that is 100, and that is 180. So my slope of the line is 100 over 80, which is 5/9. So I have y equals slope x plus b. I'm going to take a specific value. I'm going to take that one right there. So when y is 0, we have slope times 32 plus b. b is negative slope times 32, which is negative 5/9 times 32, which is negative 17.7. And so the temperature becomes degrees Celsius equal to the slope times the current temperature plus our intercept, which is negative, which is 23.88 degrees Celsius. To get to Kelvin, we add 273.15. And so this is 297.038 repeating Kelvin. It is not degrees Kelvin, it's just Kelvin. So now I plug into here, so divide by 273.15, square root 331.3 times, and we get 345.5 meters per second. So that is the speed of sound. So if I take the red tube and I'm swinging it around, we need a length of it. So something tells me that last bit did not actually record, but I took the red tube, I lined it up against the meter stick, and I measured the length. And the length, there's a certain amount of flexibility there, but the length I got is 80.0 centimeters, or 0.800 meters. So if we were looking at the first harmonic for the red tube, the first harmonic, it's open at both ends. So if that's my length L, this is a half of a wave, so L is equal to a half of a wavelength, and therefore the wavelength is equal to 2 times L, which is 1.6 meters. So now I know that the speed is equal to frequency times the wavelength, and so the frequency that we would hear would be the speed over the wavelength, and the speed that we found was 345.5 meters per second divided by a wavelength of 1.6 meters, and we get a frequency of 345.5, 1.6 divided by, of 215.9375 hertz. That's 1/seconds, so hertz. So now I'm going to go to the online tone generator, and I can now play it down to certain decimal points, so 215.9375, and this is what it sounds like.
937.
That's definitely not what we heard when we were swinging it around, because this frequency is not able to be produced. It's the next one that we care about. So let's take a look at the next one. So this is the second harmonic, where the length is equal to the wavelength, and so therefore the frequency we should hear would 345.5 divided by 0.8 meters. So it should basically be twice that, which is 431.875. Two sounds are going to be just naturally different. There's something known as the tone of the sound. Just one's being produced by a speaker on a computer and the other one's being produced by a plastic tube. So there's naturally some differences. So we're looking just for the essence of the frequency there. Anyway, that's a caveat. So let's play that note. The next harmonic, so again we're adding a half wave every time. That's one wave to there, so this is 1.5 wavelengths. So L is equal to 3/2 of a wavelength, or 1.5 wavelengths, or the wavelength is 2/3 L, which is 2/3 times 0.8, which is 1.6/3, which is 0.53 repeating meters. And so therefore we have a frequency that we would hear for the third harmonic would be 345.5 divided by 0.53 repeating, so 345.5, and I get 647.8125 hertz. So let's play that. And now the fourth harmonic, we're adding another wave, so L is going to be equal to 4/2 of a wavelength, or 2 lambda. So the wavelength is going to be 1/2 L, which is 0.4 meters. And so we get 345.5 over 0.4. This is the speed is equal, the frequency is equal to the speed over the wavelength. And this is 863.75 hertz.